Welcome to MakaiPlan Pro, the world's leading subsea cable lay simulation software. In this video, we'll show you how Makai can help you automatically adjust your cable engine speeds to lay down steep slopes, lay your cable and transitions with the designed amount of bottom slack, adjust your ship waypoints around altercourses to ensure that the cable is laid close to the planned route, and calculate instructions to minimize the amount of bottom tension during repeater deployment and touchdown. We'll also show you how Makai can automatically calculate your as-laid path and body touchdown positions from your model solution data. In this example, we'll run the look ahead with auto slack to automatically adjust our cable payout speeds in order to lay the cable down slopes exceeding 20 degrees with a planned amount of bottom slack. We've set our bottom slack goal to be 0.5% as we are laying double armor cable, which requires a minimal amount of slack. We can see the future cable shapes calculated by the look ahead displayed in green in the 3D viewer. After we've checked that our auto slack solutions all achieve our slack goal, we can accept the look ahead to have these optimized instructions added to our ship instruction set. These instructions will be sent to the DP and cable engine operators. In the plan view, we can see the DA/LW label behind the ship, showing that the cable transition is in the water. We've set the look ahead to automatically run every 40 minutes and with a duration of 60 minutes. This ensures that we'll always have optimized ship instructions. The look ahead is a powerful tool used to forecast future cable touchdown solutions based on a given set of instructions. When run in manual mode, the look ahead will use the instructions at the top to calculate the future touchdown conditions and cable shape if the instructions are followed. The look-ahead cable shapes can be seen in the 3D viewer. When the look-ahead is run with auto slack, it will keep the ship speeds and waypoint coordinates from the instructions at the top, but will automatically optimize the payout speeds in order to achieve the slack goal you have set in the Parameters tab. You may also want to run the look ahead with auto tension to calculate your cable payout speeds in order to lay your cable with the planned amount of bottom tension. This is common when laying power cable or stiffer fiber optic cable types. The added curvature you can see at the cable touchdown is due to the bottom tension that is being maintained as we set it in the look ahead with auto tension. If we run the look ahead with an auto slack goal that is less than the planned slack, our bottom cable in hand value will increase. Bottom cable in hand represents your inline accuracy of your cable lay. For example, if your bottom cable in hand value is negative, this means that the cable distance of the section of cable that is touching down in the model solution is greater than what was planned in the RPL, and making your slack goal in the look ahead less than your planned slack will help bring the value back to zero. You will want to keep your bottom cable in hand close to zero to help ensure your cable is being laid as designed and your repeaters are landing close to their planned positions. Also note that bottom cable in hand increases when cutting corners during altercourses. We can also check the Cable Segments tab of the 3D viewer to view the coordinates, depth and other values relating to our cable transition or any other segment of cable in our dynamic cable shape. Toggling back to our look ahead, We can see that AutoSlack has finished calculating our optimized payout instructions to achieve our slack goal of 0.5%. The slack goal we set was less than our planned slack of 4%, which we can see has caused our bottom cable in hand value to increase. By looking at the 3D model solutions, we can see that our touchdown cable type changed from double armor to lightweight. The cable transition touchdown may also be observed in the 3D viewer. We will now change our AutoSlack goal to be the same as planned in the RPL. Notice that our bottom cable in hand remains the same, as our slack goal matches our planned slack. As you can see, we've adjusted our ship waypoints to ensure that the cable is laid with minimal off-path values around the altercourse. We'll show you how this is done later in the video. As our dynamic cable shape further develops and we enter deeper depths, we can see our layback is increasing. When the look-ahead is run, we can also see the look-ahead as laid path in the plan view. This shows where the cable will be laid if the DP and cable engine follow the optimized look-ahead instructions. We can see that because we've brought our ship path slightly off-path in the opposite direction of the altercourse, our cable will be laid off-path in the starboard direction before crossing back over the planned route and laid along the port side of the route. We can also see the dynamic cable shape in the water column behind the ship, displayed in the plan view. By opening the cable assembly or seeing the cable to next body value in the model solutions, we can see that we have a repeater deployment in about 20 kilometers. We'll cover how to handle repeater deployments later in the video. As the cable touchdown makes its way through the altercourse, we can see our cable off-path moving from starboard to port side. Once the touchdown point has passed the altercourse point of the RPL, we can see that we've gained some bottom cable in hand back by slightly cutting the corner. When running MakaiPlan Pro in plan development mode, our optimized ship instructions are automatically copied over to your ship plan to be used later by Makai at sea. As the ship in our look ahead goes around the outside of the next altercourse, we can again see the cable off-path grow in the starboard direction. To decrease this off-path value, we will move our look-ahead plan points closer to our path, then rerun the look ahead to see how the values have changed. Makai is currently developing advanced algorithms to automatically calculate the optimal ship waypoint coordinates for going around turns in order to lay the cable with minimum off-path values and with the designed amount of bottom slack or tension. Once we accept the new look-ahead instructions, the instructions will be added to our ship instruction set and copied to our ship plan. Zooming in on the touchdown in the 3D viewer, we can see the look-ahead cable shape heading in the starboard direction prior to the altercourse. We can then see the cable come back across the planned route and lay on the inside of the altercourse. The look-ahead solutions reflect these off-path values. Our maximum off-path value is about 80 meters. Also notice that we will gain about 40 meters of bottom cable in hand by cutting the corner of the altercourse. Measuring the perpendicular distance between our look-ahead as laid path and our planned route will give us the same value. We can pan ahead in our 3D viewer to view any upcoming terrain changes or areas of interest. Viewing the ship from above in the 3D viewer will show the 3D dynamic shape of the cable as we make our way around the altercourse. Our repeater deployment will be coming soon, so we will make sure our cable status window is open to tell us how much cable is left between our current roto count and the cable distance of the repeater, and how much time is left until the repeater is overboard based on our current payout speed. By double-clicking on a field in the cable status window, you can change the font size, set the number of decimal places to show, and add alarms for when the value exceeds a certain amount. Our next altercourse is small, so we've only made minor adjustments to our ship waypoints to keep the touchdown close to the planned route. The look ahead with auto slack will automatically adjust our cable payout instructions to account for the small up and down slope coming soon. Running the look ahead in manual mode will tell us the touchdown solutions we should expect if we follow the above instructions. Anticipating that the repeater will start moving about 200 meters before it is due to go overboard, we can insert an instruction to decrease the payout speed to 0.5 and ship speed to 0. This will help us minimize the amount of bottom tension during the deployment. We want to increase our ship and payout speeds again 20 meters after the repeater has been deployed. Running the look ahead in manual mode, we can see what bottom tension values to expect if we follow these instructions. We can then move the time of our first change point forward to the time of the instruction where we want to increase our speed and start laying with auto slack again. The first change point is the first instruction the look ahead will try to optimize when running its calculation. We can change the ship speed of these future instructions so that the look ahead with auto slack will account for the increased ship speed in its cable payout calculations. If we click Yes in this window, the look ahead will assume that your DP and cable engine operators will follow all of the instructions prior to the first change point instruction and will calculate the predicted model solutions accordingly. By looking at our look ahead and 3D viewer, we can see that our ship will stop with a small amount of cable payout as the repeater starts to move on deck, then will speed back up and continue laying with slack once the repeater is overboard. Once the ship stops for the repeater deployment, we can see our top angle and bottom tension start increasing. Notice that Makai was able to dynamically calculate cable payout speeds to achieve your slack goal with a heavy body in the water and laying down slope. Running the look ahead in manual mode, we can see our future cable shapes if we follow our existing instructions. You may notice that the repeater will sink faster than the cable between it and the touchdown. By selecting a look-ahead solution, we can scroll through our instructions to find the instruction which resulted in the solution. In this example, we will set the cable payout speed of the instructions for when the repeater sinks below the cable behind it to 1.7 kilometers per hour. This should hopefully slow down the descent of the repeater and minimize the amount of cable ballooning behind it. The sinking repeater will start applying some bottom tension to the cable behind it. Your job is to minimize this bottom tension while also landing the repeater in its planned position. Once the repeater's depth is greater than any segment of cable sinking behind it, it is impossible to continue laying with slack by adjusting the payout speed alone. In our look-ahead solutions, we can see that our repeater should touch down with a bottom tension of only a few kilonewtons. Running the look ahead again, we can adjust our cable payout speeds for after the repeater touches down in order to continue laying with bottom slack again. While laying your cable, or once the installation is complete, you can easily create your as-laid path from your model solution data. This is always required in final reporting for the client. The as-laid can be generated in minutes and helps to avoid human error in recording the touchdown points. Once you have created your as-laid path, it will be displayed in the plan view, with its colors rendered by the bottom slack value of each segment. You can also generate as-laid slack and body logs. The slack log provides the average seabed slack values over every 2 kilometers of KP distance. It will also tell you the touchdown coordinates, off-path distances, depths and ship slack for each 2 kilometer segment. The body log is especially important when installing a system that requires highly accurate seabed placement of sensor packages. It tells the user the touchdown coordinates, cable distances according to the roto, touchdown depths, KPs, and inline touchdown off-path distances for all bodies including repeaters, joints and cable transitions. It also tells the user the average seabed slack between each consecutive body. MakaiPlan Pro can be used for Makai lay operator training to produce detailed pre- and post-lay analysis, feasibility studies, and cost estimating. Makai Lay is an advanced subsea cable installation software that enables users to lay submarine cables with the highest level of accuracy, speed, safety, and reliability possible today, dramatically reducing the risk of cable failures. The software has been rigorously tested and validated and is used by over 80% of the global fleet of cable ships on countless commercial lays and military installations to successfully install well over 500,000 kilometers of cable worldwide. Please contact Makai to try the software or for more information. Thanks for listening.